where if you've got any questions on this module, then you can come and see me. However, you have got some material to cover. If I can say it's not important towards the exam, so that might help you whether you want to learn it now or a little bit later. And, you know, has anybody looked at the drainage online? Kind of, yes. One person, awesome, right? You get a prize at the end of the week. It gives you like a history of drainage. Talks about you know, the storm and the foul, and goes all the way through the individual points. So you can skip through the history. You know, in terms of the history of Middlesbrough, you know, a lot of the houses that you're living in around here, sort of 1930s sort of houses. Like, I don't know if you picked up, like, there was the two types of systems. There was a separate system and a combined system. Have you noticed which you have on your house?
I have a separate system.
You have a separate one. Do you know for definite?
It looks like, it seems to be.
So it looks like you've got extra two sets of pipes coming down. So one, you've got the roof sort of coming down into the gutter, and then that will go into the storm, and then that will go into a beck or a water course. It all depends on how clean everything is, and it can go to other sources. And then you've got your foul, so that's all of your poo and your wee, and the stuff that comes from the sink, and all the fat that you pour down the sink. All of that goes into the foul. Now, in Middlesbrough, most of the systems are joined. They're separate on top, but what you'll find is that they tend to go into one pipe that just goes straight into the sewer, and it all goes into in the same place. You find that all the sewage in Middlesbrough goes to Billingham. Where's Billingham? That way. Yeah. So when you go to the toilet, which goes all the way down to Billingham, it's Cowpen Lane, Billingham Sewage Treatment Works. I worked on there, just repairing the works. Like on the video, you saw there how all of the sewage goes through all the pipes, and then it gets to the sewage system in London, and it's sprayed onto slag. So all of the poo and that goes onto stones, and there's lots of bugs that are living in there, and they all eat it and play around with it to try and put air back into it. It plays around with it's called the biological oxygen demand, and but you'll learn more about that with Kieran. At Billingham, when you get there, the sewage system. They have aeration tanks, so you get there, and all the poo is in big swimming pools, and it's all being frothed in the air. So you get on site, and you're walking through this like natural sort of jungle type mist, and doing your work. And you will find that you'll be off sick for the first week or two because you're breathing in all types of crap, so you end up you get like a bit like a flu, but once you've been off and you come back, you're perfectly fine. But you will find, you know, in terms of pipe works and in sewage treatment works, and all of our water from Middlesbrough comes from Darlington and Broken Scar and Long Newton. They've got a reservoir there that they store water, and repaired the reservoir there. Like down south, when they ran out of water, all the water was sent down from Long Newton's reservoir, sent tankers so that they could fill up those pipes down there. We get lots of rain up here. But you'll find that with civil engineering, you know, are you going to be into structures, buildings, bridges? If you're into infrastructure, roads, it's highly likely that you're going to be doing some form of drainage design. And you know, Kieran Flood, he taught me, and I remember it being quite a hard topic, all of this hydraulics and that. And but it is very useful. You actually, the stuff that you learn, you'll use it in practice. So have a look through the website, get an appreciation. And when I say appreciation, don't remember all of the little, you know, the names of all the different individual items. Get to know the main sort of layouts. And so, you know, understand what a pipe is, and then you have like you've got your rainwater pipe that goes down into your gully, okay, and then the gully goes down, and into your storm sewer. So that would also pick up all of the gullies on the road also, so all of that's going down towards the water course. And then you've got the red here is our foul sewer. So again, it's going to another gully, but that's picking up all of like sort of your kitchen waste, etc. And then you've got your toilet that's shooting down all the stuff down into there. And you know, everything goes down there. It's especially the foul sewer. It's Holy Island. I do a project. If you're in the MN, you'll do a project there with Holy Island, and I think there's only about 400 residents on the island. But when it comes to summer, they can get like 2,000, like a day sort of like coming. And when they all arrive in their buses, there's only like one set of toilets, and they got off the coach, and they put jeans and bags and nappies and everything down the toilets, just flush it away because it's like gone. You know, like that's what we do with drugs, isn't it? When you want to like get rid of it before the police arrive. So everything goes down the toilet, and so you find that you have to design your sewage system to cater for the days when not many people need to do a lot of business, and then you've got the days when you get a lot of people who arrive and everything gets sent down. You've got to make sure it doesn't flood. And so you'll find that some of you, it's highly likely that you're going to be working with, highly likely that you'll be working with drainage, whether you get into sewage treatment works or water treatment works. You'll find that when you come to do design, you know, when it's snowing today, you know, you've seen in the news about all of the flooding and stuff like that. That's where they've designed the drains to cope with a particular amount of flood. You know, the Environment Agency have been on saying, and some of you might work for that Environment Agency if you stay here. All of the flood management systems have been designed fine based upon anticipated floods. And what you'll find is that you'll sit there and think, okay, so what was the biggest flood that we've had in 50 years? Well, it was this deep. So let's make our embankments this deep to try and cater for it. But if the council's got more money and they say, well, okay, well, let's design it based upon the last 100 years. So in the last 100 years, there's bound to have been like a much larger flood. Like if you go back 4,000 years, like to Noah's flood, where that flooded the earth and wiped out all of humanity because of all your sins and that, that's a bad flood. But the problem is that we as engineers can't really design a pipe system for Noah's flood. So when you come to design something, you have to choose, do I design that flood based upon the biggest flood in 2 years or the 1 in 50? And you find that the further you go back, the bigger the flood. And you know, if you lived at house number 1 and I was going to build house number 2, like you've got to appreciate your neighbours also, because when it starts raining, normally when it goes into the ground, it soaks away. They say that 40% soaks into the ground and 60% of it will make it into a gully. But if that was all grassed land and I built my house there so that the water on the roof was going straight down the pipes, and if I decided to concrete everywhere, where the water normally soaked into the ground, the water now arrives on my site and then flash flood. The flood goes much faster into this area. Now we have to sort of do a little bit of a design to make sure that your house is not going to send water down much faster. If it is, then you have to end up sort of putting these attenuation sort of tanks in there. Like a good example is it's like a swimming pool. If I built a swimming pool, every so often you've got to empty a swimming pool. You don't just unplug it and let the water just go down the system, because the pipes couldn't cope with it. So they tend to go into tanks, and then it's let into the system at a rate that the pipes can cope with, and that you've agreed with the Environment Agency. The video went through some typical components of a drainage system, and I think if you look through one of the exam questions, you possibly have to draw the layout of a drainage system or talk about the problems of a drainage system. So again, you've got all the, the rainwater gutters, and like you probably won't be involved in designing toilets and pipework within the house. It may be that you will, but a lot of times it's the mechanical engineers who will do that. And there's a British standard that you have to count how many days there are and how many showers and how many toilets, and then you can work out that if it was a day when everybody decided to use everything at the time, then you could design the whole system. But it's usually mechanical engineers when it comes to larger projects. For houses, the size of pipes tend to be standardised because we tend to do the same type of things in our houses. So gutters and the down pipes and that, they're all standard sizes. And you'll find that most of the drainage that we choose for a house tends to be the same. There are rules about a minimum amount of gradient. If it's too shallow and the water's moving really, really slowly, all the things that you put down the pipe will, if it's not going too fast, it'll stop a little bit. All of the sand, all of your sweet corn, you go to the toilet and everything sort of flows down, and all of like your sweet corn and baby wipes are a drain's worst enemy. What's those things that you don't put in your ears?
Cotton bud.
Yeah, cotton buds. They're a nightmare. So putting them down, anything that you sort of put down, it can get caught within a drainage system. And you need a gradient steep enough so that the water flushes it away. So water goes in. You've got various types. Talked about sort of gullies, and talked about these traps, like it's like a U-bend, and that's on like sort of toilets. It's just to try and stop any smells in the pipe system coming up back into your toilet or back up the gully. Like if you find that your gullies on the ground smell, it's because the trap is probably cracked and the water that's normally there is drained away, so all of the smells can come out. So it's said about every time you change direction, or every sort of 30 metres you put in a manhole, so that every so often you can open it up and have a look and see if it's blocked or not. Usually you can get a blockage in a change in direction, so as everything's flowing down that way, you could have a bit of a build-up there, and then it could get blocked. So you'll find that this is why you have inspection chambers or manholes. Normally these little plastic ones are called inspection chambers. Once you get like over a metre and you've got to get into a hole, so you've got a man in a hole, then it's usually sort of built of bricks. So it doesn't really matter whether you call it an inspection chamber or a manhole. My worst manhole experience was it was the Billingham Sewage Treatment Works. So I arrive, I am a brand new graduate, and I get on site, and the contractor has excavated down 2 metres, and then built a brick manhole, and then he's covered the whole thing back up. And he's done that 20 times. I turn up on site with my drawing, look at what's been done. It wasn't my job. The other engineer should have noticed this. But I turn up on site, look at my drawing, and I realise that the contractor had used the wrong type of bricks. So therefore, my first instruction on my first day as a new graduate was to tell the contractor, you have to dig all of those 20 manholes out and replace them. It takes a certain type of person to work on site, and normally you go with your mum or someone just to be an authority. But yeah, so they're the main things to have in your head if you had to do a design. It talked about the different types of some of the different problems that you can have on site, and you've got this drawing. You've got this drawing in your handout. I haven't got it. So SVP, soil. So rather than foul, they call it soil also. So you've got the soil vent pipe. And normally when you've got your V, so either your poo goes down a pipe called the soil pipe, but if there's a vent on the top, so there's a pipe at the top called the soil vent pipe. So off the poo goes, just gets to that corner, it starts getting stuck because there's not a manhole there. You need a manhole here. So if you want to draw that in, because it's a changing direction, we've got a gully going in, that's perfectly fine. And then we're going around the corner. You've got a kink in the pipe. That should either be straight, or you could put another manhole there. In terms of the tree, that can be a problem. As all of your poo and everything is going down the pipes, it gets nice and warm inside of the pipe. And because it's warm, all of the cooled ground, all of the water in the cooled ground condenses. You know when you get water condensing on a window, all of the water inside of the ground condenses around the outside of the pipe. And the tree senses that, starts sucking its water from the outside of the pipe, and then starts messing with the drain, and it ends up breaking, and then ends up getting into the pipe. So a tree can't like think, "Ooh, there's water in that drain pipe." It's just that's the way it works. So the red goes into the foul. When it gets over it, when it gets past your last manhole, it depends on the drainage company, but that could belong to you until it reaches this manhole, and then it belongs to Northumbrian Water. So in terms of who's going to repair it. Bit of a problem putting a manhole on a driveway. You've got to make sure that the cover is okay for cars going over. I've had a crane and I've had a cherry picker go over a manhole and then tip over because it's broken into. So that's something to be careful of. And then, right, so that's, and then the last red one is you don't put the toilet into the storm, because the storm goes into water courses. I worked on a job in London at Pims Park. There, somebody connected sewers, so pooey stuff, into the storm. The storm went down into Pims Park. So imagine some pipes going into Albert Park, and the whole pond just stinks, and you've got a lot of like ladies' products and that just floating like on the top, and nappies and everything. And, so that was a job to try and sort of sort out. Blue, again, rainwater pipe travelling down. This branch should be really going in the right direction. Otherwise, it's going to create some blockage at that point there, and it travels all the way down. You can put a manhole there. You can put things like this RA is a rodding eye. That's where you can get some pipes and unblock your drains. It costs £30 if you want to get yourself some rodding. Also doubles up as a chimney sweep, and they're really cool too. Right, that's an overview. So I've given you a quick overview of drainage. So when you look at that topic, don't get too deep into it. Right, if you go to the front of your handout, you've got Chapter 9 has been digitised, photocopied by the library. It's a yellow book called Civil Engineering Construction. It's quite a useful book. It covers like retaining walls, which I think you'll be designing next year. So I think it's called Civil Engineering Construction, and it's by a guy called Warren. And I don't know if it's Warren Dean, D-E-N-E, or whether his name's Dean Warren. I think it's Dean Warren. So if you look at Warren, and I'll give you the full chapter, but just to make sure that you get all of the notes with regards to these calcs, that's why you have this this chapter. So I'm not going to read it all out, because that would be totally dull. but I'm going to try and explain what's in there. So going through, and you can highlight certain bits. So has everybody got the page? Has everybody got the page where we're starting at? It's just over the blue page. So, at the beginning of the chapter it says, drainage can be roughly divided into two categories. So you've got surface water, or your storm drains, and then you've got your foul drainage, which gets rid of your sewage. And when you come to design them, you'll find that the principles are exactly the same. Now down here, what we're going to focus on, on storm water rather than sewage. Now, when you come to design drainage, there's the three sort of stages that you go through is one, you do a hydrological study. Now, what that means is that you go to the Met Office. We always call it the Met Office because it's the meteorological. Yeah, too many syllables. Can't say it. There's a few words I can't say. Can't say it. Yeah, and something else. But the Met Office, I can spell it. Isn't it awful when you can't pronounce a word? You've got a presentation this week. If you can't pronounce a word, don't stick it in your presentation. I always think Lay down.
There's just no in between.
That's all one word. But yeah, look it up on and check the spell check in, please. It doesn't really matter. That's why we call it that. That's why I call it the Met Office. So you go to the Met Office and you say, I'm going to be designing the drainage in a particular area. Can I have the history of a particular area? So please, over the last 100 years or more, they've been collecting how much rain there has been. Does anyone do a rain collector at school? No one ever, what, you didn't go in the garden or Blue Peter type thing where you do that in overseas? Do you have, it depends if you have rain really. But this is where we used to put a glass outside, and then when it used to rain over a particular amount of time, then you'd measure how much rain there was, and because rain is measured in millimeters per hour. And oh, you missed out on so many exciting things. Yeah, don't think Cambridge does that yet. It's definitely first year stuff. But if we're going to be designing the drainage, like sort of for this area, we go to the Met Office and say, okay, can you tell us what is the rain? And these are like the typical sort of charts that you have. So in October we had 110 millimeters per hour. So this is like for a particular year. And then you say, can you please tell me what was the biggest storm so then I can design my drain? So after the Met Office, you then need to do your design. Then after you design, you then specify types of pipes, types of manholes, etc. When the rain comes down, it lands on an area called the catchment area. So it's like a big net, and usually you would use like AutoCAD and all the levels to try and work out. Like this example here, in this booklet, there's going to be a dam here, and they want to try and work out what's the catchment area. And it works out, this is the area, and you measure it in hectares, and all of that goes into that area. Like in Middlesbrough, all of the water arrives everywhere, and it comes down a number of banks, and they go into culverts, and if there's too much water coming down, it all goes into Albert Park Pond. I don't know if you know that. The pond itself is been designed. So there's our pond. It has a particular volume. So when there's loads of water coming down, raining everywhere, because the pipes can't cope with it, what happens is that it fills up Albert Park Pond. Now, civil engineers, weren't maintaining the pond, so after a number of years, the bottom of the pond was full of silt and shopping trolleys and you name it. Hey, I tell you what, is it, you know when you see people fishing at Albert Park? Like I saw a guy get a fish that big.
But they have to throw them back in, and we were walking through, and a barbed hook got stuck in my shoe, and that's illegal in the park.
And they didn't throw you back in. Right. Okay. So in terms of the pond, so it got filled up, and then when there was a flood and all of the water came down, because the volume was already filled, there was only this amount of volume left, and what happened is that all the water arrived, it raised, and then all of the area around sort of Albert Park flooded, and so what they did, they had to get contractors in and empty the silt out the bottom there to allow for the pond to act in the way it was designed. So that's the catchment area. And then you would say, okay, so what's the typical sort of millimeters per hour? And so it gives you like an example here, and you know, and it says like sort of that we have to refer to table 9.1. So if we jump over the page to this one here, this is a typical table that you would get from the Met Office. And it'll be different ones for different areas, because it rains loads in Scotland, not at all in other places, and not overseas, because you've never done a rain gauge. But if it rained for 5 minutes in an area, and you're going to be doing a design, you have to pick off what the millimeters per hour is. And like if we looked over the last, if we looked at five minutes, if we looked at the largest storm in the last year, you would expect 50.8 millimeters. If we looked at the storms over 2 years, got 63.5 millimeters. And if you looked over 5, and then if you looked at over 100, it'd be much larger. Or if you go all the way back to Noah's flood, massive amount of water. So this is the type of table that you get. So it gives you an example. It says, for example, if you look at 2.5 minutes, then you're likely to have 80.9 millimeters per hour once in every sort of 2 years. So it just tells you where you get your information from to put it into your formula to work out your flow. Now the rain arrives, and it doesn't all land in the gully. You'll find that rain, if the gully was here and the rain arrived across there, we have to time how long it takes for that little drop of water to make it into this gully. Because once the furthest point has reached that gully, then all of the water, then you know that you're at full capacity, all the water would have reached. So what you have to do is you have to look at something called the time of concentration. The time of concentration is the entry time, so that's the time for that little drop to make it into the manhole, the furthest one. And then the time of flow is how long it takes to get along the pipe. Now there is another table. It's table 9.2. You don't have to use this. So can I say that in the exam there are not many questions where there are calcs. I can't think of any questions that we've done with calcs. This is one of them. So make sure you get your head around this topic. Table 9.2. What that does, it talks about how long it takes for water to get into a system based upon the type of gratings. That's too much detail. For a civil engineer, what we used to do is, and what we still do, is that there are a number of documents you can refer to, but it's got an example at the bottom of the page that says we use the TRRL contractors report, and what that says is that it takes 5 minutes for some water to get across a car park. It takes All right, 5 minutes for,
And 3 minutes for highways.
in 3 minutes for for a highway. So we just say, okay, our entry time is 5 minutes, and then we have to work out the time of flow after that. Okay, so we don't use table 9.2. I've given you some formula, and I've given you most of them written down here. So we use something called the Lloyd-Davies formula, which is this one here. So you want to highlight that. So that's the formula is flow, or runoff quantity. It's the amount of water, that's Q, equals, and then it's a fixed constant, so it's always 3.610, times by the area of the catchment area. So it's the area that the rain's arriving on, and that's in HA, hectares. So if you've got your area in meters squared, then you can divide it by 10,000 to get it into hectares. I is the rainfall intensity. I is what we get from table 9.1, so that's the millimeters per hour. And then P is how much water after when stuff's soaked in makes it into the system. So it says 1 for highways. Now what that's saying is that if all of the rain landed on a highway, 100% of that rain would make it into the gully, so we times it by 1. If it landed on grass, we multiply it by 0.6. Now what that is saying is that 40% of the water will soak away. 60%, 0.6, of the water will make it into the drainage system. So when we come to do a design, if it was a highway, you have a lot more flow than for grass. So then before we get into the table also, so we've got the Lloyd-Davies formula, Q, and like some of you would have done some physics or some other type, where if you want to write these down, where you've got flow is our volume over time. So flow is usually measured in meters cubed per second. And we'll be rearranging that to work out the time, which is the volume divided by the flow. And then also you've got velocity, how quickly the water will be flowing through a pipe, and then depending on how quickly it flows through, that's the how we can work out the time of concentration. So velocity, it's in meters per second, so it's distance divided by time. We will rearrange that to have time in seconds. So, and if there is an example like this in the exam, you will be given these formula. You've just got to know how to use them. So carrying on down that page. So we've got our Lloyd-Davies formula. Then just below that, once we've got our flow, so we've worked out how much water, then we need to design the pipes. Now, when we look at the pipes, you have all of these K values. Now, what the K values represents is, depending if you had just clean water, it would flow nice and easy. If there was lots of sweet corn and Mars bars and everything else flowing down this pipe, then it wouldn't flow as well. So therefore, you have a different K value. And you also have K values depending on the type of pipe. If you have a nice smooth plastic pipe, you have a particular K value. If this is a corrugated iron pipe, so it's very rough, so the water coming down it, it would have to be more storm water because of everything that could catch in the pipe. So you've got these K values. Once you know the type of flow and the type of pipe that you're going to use, then you have your K value, and then you can get your table, and there are a number of tables to look at for each type of pipe. And I'll explain this table. So if you want to get yourself on this table, this graph. Right, we're in concentration mode. Right. The vertical lines, that is the gradient of the pipe. Okay? And I've given an example, written an example there, and I've also put it up here. Like on the video, it started talking about the cover level. That's the level that the ground is at. And the cover is the cover for the manhole. We've also, have we done this in surveying at all? Invert levels. You know, you're measuring a level of something. Your invert level is the bottom of the pipe or the bottom of the manhole. And if you had two manholes and there was a distance of say 30 meters, so putting it in millimeters, you've got 30,000 millimeters. And if the distance in height was 150 millimeters, then you can do height divided by distance. 1 over that gives you the gradient that the pipe is at. So this pipe, for this example, is 1 in 200. So that's how you'd work out what the gradient is. Now, it depends on where you live. Sometimes you can specify a gradient and say, I want all my pipes to be of this angle. But what you'll find is that if you come to build a building in that corner over there, you're working with the lie of the land, and you know that there's a drain over here that you've got to get everything into. So that's fixed, that manhole there. I'm going to be building my new property over here. I have to work back from the depth of that manhole, and I have to make sure, and it could be like 1 in 100, that I'm coming up to the bottom of this manhole for my house. So you'll find that a lot of times you're quite restricted on the gradient itself if you're joining into a system. So there's an example for gradient. What else do we have? We've got the horizontal is the discharge or the Q per second. So a pipe can take 10 meters cubed per second, 20, 40. So that's what the horizontal is. And the diagonal, this one here, is the size of pipe. So that's a 150 diameter pipe, 225, 300, all the way up to a 2.4 meter pipe. So we've got small pipes, big pipes. That's the diagonals that way. The diagonal this way is the flow through the pipe. So this is the velocity. So it's got written here, average velocity in meters per second. So these lines here. So to show you an example of how we can use this, and it's written down in the text. We'll go through an example here. So if we had a pipe that was 150 diameter, so we would highlight this one here. If our gradient was 100, so you just draw up to that diagonal line, then at this point here, our average velocity of the water going through this pipe is 1 meters per second. And if you go across, in terms of the flow through the pipe, it would be about 18 meters cubed per second. So that's the flow, how full it is there in the pipe itself. If our gradient was still 100, but if we went for a bigger pipe, so if we go up to here, then the average flow would be 1.3 through that pipe, and it could take 50 meters cubed per second, liters per second. So that's how you would use it. Now, in the text, we are given two examples, and I want you to make sure that you get your head around these two examples. The first one is talking about there's a gully draining a car park, and the car park's 880 metres squared. So we'll just draw this out so we can visualise it. Personally, with this topic, in terms of exams, trying to visualise what the question is saying can sometimes be the difficult thing. If you draw out what you think the question is saying, so reading through, so we've got an area of 880 metres squared. It says that there's a time of entry of 5 minutes. So our water drop lands on the outside of the area and starts making its way to our gully. There's our gully. And then it says that the first manhole is 30 metres away. And it's this pipe that we want to design. So all the water is coming in, and slowly it'll be filling up. By the time that drop gets into there, and by the time all the water gets onto the end, then this pipe is going to be at full capacity. So when we come to do the design, we're looking at whether it can cater at the end of the pipe itself. So all we're doing is working with the Lloyd-Davies formula. So we're aiming to fill in this Q, 3.610, and if you look at the formula, where it's multiplied by the area, so we've got 880 metres squared. We divide by 10,000 in order to turn it into hectares, so you always must do that. Then you times by the I and the P. Now the P, it's a car park, so it said that I is 1 for a car park or 0.6 for grass, so we're using 1. So in terms of the time of concentration, you've got, so if we had a 150 millimetre pipe, this is what we're going to propose. So it's a 150 diameter, and we're going to put in a gradient of 1 in 100. So that's what we're proposing. So therefore we go to our table, we look at the gradient of 1 in 100. We go to our 150 line. We can go and pick off that our average velocity is 1 metres per second, and also we've got the full capacity of the pipe, that they can take 18 litres per second. So the time of concentration equals the time it takes to get into the gully. So what is it? 5 minutes. That's how long it takes to get from there to there. 5 minutes. And how long does it take to get from there to there that we've got the full capacity? And this is where we use our formula here. Velocity is distance divided by time. If we rearrange that, time is distance. Our distance is 30, and our velocity of this chart is 1. So it's written here, the time of flow along the pipe is 30 metres divided by 1 meters per second. That gives us 30 seconds. So it takes 5 minutes to get from that point to the gully. Then it takes 30 seconds, which is 0.5 minutes. So it takes 5.5 minutes for all of the water to get to the end. We take that 5.5 and look at the typical rainfall intensity. So we go down, this is the table 9.1, so we go down to 5.5. What's the storm? What does it say? For 2 years. So looking at 2 years, duration 5.5, going across the 2 years, we get a value of 61 millimeters per hour. So over 2 years, we've got 61 millimeters per hour dropping on there. That's our I value. So putting it all in our formula, again, the fixed factor times by the area, times by our I value, times by the P, which is the concentration. The difficult part is you know, I think if I was, you know, if you're working through this, start with this formula, and then you start putting in the AI and P. And the P is easy, the area is easy as long as you remember to divide by 10,000. And then you've got your I value, you need to get how long it's taken to get into the manhole. Now, our Q value is 19.4. So the amount of water going through is 19.4 litres per second. That's the amount of flow going through. When we look at the capacity of the pipe can only take 18. So this pipe can only take 18. Therefore, it's going to be full, and therefore it's going to fail. It's going to back up and flood. So what can we do because it's failed? We can either increase the gradient and keep the same size pipe. If we increase it, and so if we increase it to 140, it means that the capacity of the pipe would be around about 30. So we can either steepen the pipe, or if we're restricted on the gradient, we can go from a 150 to a 225 pipe. So if we go 100 up to a 225 pipe, that will allow us to have 50 litres per second. And, so you've got to go through the whole process again to try and work out what flow would go through. But you find that a 225 pipe should be okay. Like if we do have a pipe, again, our pipe, it can take 18. The flow was 19.4. So 1.4 of that stuff's going to be going elsewhere. So we need a bigger pipe. So a bigger pipe, the 225, could take a lot more. So all of your flow is going through this pipe. We tend to design pipes so that they're 80% full. We don't design them so that they're 100% full. That's just a little bit of a safety factor. That's the basics of designing all pipes. And I'll show you lastly, I'll show you one other example, which just takes this forward. This example 2, it says it's required that we design the pipe shown in this system. So I've drawn it here also. So we've got a car park, and it's 100 by 150. This area goes into drainage channels, and that's like a drainage channel. I don't know if you've seen these. Like, you know, when you walk outside and all the rain's landing on the ground out there, and there's some little slots, like a little metal slot, and they're sort of discrete hidden drainage channels. We don't design the drainage channels, but all of the water lands into these drainage channels, which is like represented by these like blue arrows here. And all of them send it into this first manhole. So all of the water in that area will go into there. Then it starts going through the pipe. By the time you get to this manhole, you've got the water that's flowing through from this area here, plus the area of all of this water via all the channels going into that pipe. So we've got a nice small pipe, next manhole, bigger pipe, next manhole, bigger pipe, and then you've got outfall into like a water course or a beck or other. And this table that you have goes through, I think of all of the tutorial sessions that we have, I think this is probably the main thing that people would maybe come and ask questions about. But we'll go through this table. And this is the Wallingford procedure. When you get into industry, you'll use a table like this to design drains. If it's a big system and if the company's got some software, the software is like called micro drainage, yeah. And it's based upon this this theory. So we have the table itself, it's all set up where you've got the manhole pipe A to B. So what we're going to do is look at this pipe here first, and that pipe there is taking in that area here. Now these here, if you know what the invert level is or the depth of the manholes, then you could work out what the gradient is. But in this example, we're saying that the gradient is always 200. Okay, so these columns are empty because we don't know what the invert levels are. We're just saying that the gradient of this pipe is 200. Its distance is 50 meters. And all we're doing is getting to this point, runoff quantity here. This column here is your Q. So I don't know if you want to write in there Q. So that's that same one formula. This is in order to put everything into our formula, Q equals 3.610 times by the area. So if once we work out what the area is, so the area of this first section is 50 times by 100. So the area is 5,000 meters squared, divided by 10,000, puts it into hectares. So that's where that 0.5 is. So the hectares is 5,000 divided by 10,000. Right, let's go through this first line. So pipe A to B, distance 50, gradient. We are assuming that we could use a 150 diameter pipe, 115 centimeters. That's how wide it is. So that's an assumption based upon that this information here. So if we looked at our table, so we've got a gradient of 200. So we go along to the line 200. We go up until we reach the pipe 150. We take the average velocity. The average velocity is 0.7 meters per second, based upon then the time of entry is 5 minutes. So our time of concentration is the time it gets along the pipe. So if you did 1 divided by the distance, you get your 1.2. Add 5 minutes, you get your time of concentration. We're saying that we're looking at a return period of 2 years. So if we take 1.2 minutes into that table 9.1, then we'll find out at 2 years that our rainfall intensity, our I value, is 58. So we now have, in order to work out Q, we've got our area, our I value, and our P value is 1, and it ends up with a value of 110. So you've got 110 litres per second going through that pipe. Looking at the pipe itself, at that gradient and that diameter, it can only take 13. So 110 is going to be going through. It can only take 13, therefore it's a fail. So what they do, they move to the next sized pipe. So it's the same details. So rather than ever 150, they go to a 300. And as they go through, once again, they find out the Q value is 110, but it can only take 77. So when you go up and have a look at here, it can only take 77 from the charts. Therefore, it's failed again. So therefore, we move to the next size of 375. That's the size of pipe. And when you go through this time, you find that the pipe is 110 litres per second going down through it. But when you look at the capacity of the 375 and 200, it can take 140. Therefore, a pipe at 375 diameter pipe at 200 gradient is okay. That's those first 3 lines. You have to guess the size of pipes and then see whether they work. Once you've done your first pipe, then you have to move on to the next one, this one here. When you're looking at this pipe here, what we've got the time that it takes the water getting from here all the way through to there. And we've also got the time that it takes for the water to get from there through there. And you take the largest time, so when you're looking at BC, we are looking at our time of concentration, again, is 5 minutes plus the 30 seconds it takes to get along there. And because we've got a pipe of 375 here, you can either, your next pipe size could be 375, or in this example, I've gone to the next pipe size of 525. So they've gone from a gradient again of 200 up to the 525, worked out the average velocity, and worked all the way through, found out what the flow is. So the flow through AB was 110, the flow through BC is 210, and that's and it's an okay capacity. And then the last one, it gives you 2 different pipe sizes, and the first one looks like it's okay, but it fails because it's over 80%. And so it hasn't got that factor of safety. So therefore, we should be going with a 600. So we're going with a 375, 525, and a 600. 375, 525, and a 600. In your own time, look through that formula, that small example. That small example is is taken to the next stage in this table where each row is just that example repeated. Make sure that you can design a drainage. Once you've got your size of pipe, the next so many pages that I've put in there, depending upon if you're in a field or if you're going to be in an area where you're going to be riding your car across the pipes, will determine how you what you put your pipes in. Like normally you excavate your hole, you put some gravel in, you put some nice gravel in to put your which it's like 10 millimeter gravel, and you put your pipes on, nice bed for the pipe. If you have a big stone underneath your pipe, and if a car rests on the ground, it snaps the pipe where the big stone is. Therefore, that's why you put the pipe on the pea gravel. And a lot of contractors prefer not to put it in. So normally the building control inspectors want to see the drainage before it gets covered. If you've got a vehicle that's going to go over, you can have concrete over the top of the pipe. If your drains are below the foundation, so if the foundation of your house creates pressure on the pipe, then you can coat your concrete coat your pipe in concrete. So there are different methods that you can do. So okay, have a bit of a look around at the construction of pipes. We talked about like manholes around the house. Manholes can be massive. You can have 3 meter sort of wide sort of manholes, and look at how you would put them in the ground, and but particularly look to see how they're designed. If you've got this page in your handouts, it's just saying, again, depending on which highways authority you belong to, it's setting out that you go to a certain depth, how you lay your pipe in the ground. Don't get into that much detail in the chapter. And the video covered a lot of the issues of putting pipes through foundations, so that if the house drops down, it'll snap your pipes. So you have to have all these rocker pipe, and you have to have like at least a 50 millimeter gap around the pipe work. Did anyone do drainage when we looked at the building regulations? No one wants to admit it. Remember we did the building regulations? Yeah, someone would have done drainage, so you would have picked up some of these points. Okay, in terms of the drainage, it's quite straightforward. It is an important part of your civil engineering career. There was your first little bit of calcs for this module. So come and see me when you've had a look at the table if you've got any questions regarding it. Can I say also just for the exams? Like today we've covered drainage. Now I've covered like house drainage and some calcs. Last year I did dams, so I did dam construction, different types of dams. We didn't do that this year, so if you look through the exam paper and you realise that there's a question on dams, then you wouldn't get a question on dams, because you will only get exams based upon the material that we do in class. So when you do look through the assignments, the exam papers, and you realise, well, we've not done anything on that, then it's highly unlikely that you're going to be getting it.
It's annoying.
Unless I've totally forgot. But
What you were reading about dams this morning.
did you?
Yeah. Just because you put like it's like an extra on Blackboard that
Yeah.
about dams. So
But you never know. You never know. It might be. I can't remember. Actually, I'm going to have a look to see what's on the.